Hello, I am Syntax Sugar, and today we'll be looking at some algorithms, and that includes binary search. So, some intuition for the problem. Imagine a library, and every single book ever written is arranged in a long straight line alphabetically. How would you go about searching for your favorite book? The Lord of the Rings, The Return of the King. So, there are many, 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 many books, and we know that it would be very hard to go through each one. So I want you to think about the most efficient way to find any book in this like alphabetically arranged list of books. So the regular approach and the first thought that might come to your mind is to just look at them ordered from A to Z, and it eventually finds the book, but we can do much better. And when looking at it in terms of like averages, so like if we take a random book, how long it would take, we usually have to take like half the library. And in terms of scaling, like with every book we'll add, it's going to add another book that we're going to have to check through when searching through this. And this gives you just kind of a bad ability to scale. On the other hand, we have binary search, and this is the approach that's most commonly used. And we know our list is ordered, and that's the precondition for it. We, if we choose like the middle one, and we can know that, let's say we have the letters A, B, C, D, E, and F. If we take C, and I know my book starts with an E, I can then just go to like the letters after. I don't have to check through A and B. So it's just kind of goes through the middle, and it makes use of the fact that we know that it's order, that it must be either after it or before it. So in just checking one book, we're able to remove half of the library as possibilities for searching. And you can see it here without any numbers, is that we start in the middle, we look at that, and then okay, it's in the middle, half in the first half. Then we look here, and then we know it's in the second quarter, and then it's in the third eighth, and then you go so on and so forth until you find your thing. And here, you can actually realize that it's going in powers of two. If you can see, it's one half removed, then one fourth, then one eighth, then 1/16th, which is our element. And in terms of scaling, it'll scale logarithmically with like a logarithm of two, as you could see, going from two to the eight to 2 to 4 to 8 to 16. And you can see that in the like graph. In big O notation, we look at how it scales with the input size. And O of n is time will increase linearly with respect to input size. However, log of n will increase very slowly, even being comparable to O of 1 at most starts. And this big O notation idea is a very, very big idea in computer science, and it's used to usually rank algorithms, such as searching algorithms, sorting algorithms, to find the best big O that we can find and accomplish. And I wanted to show you this in terms of code, how it would look just searching through. And Python has an already implemented binary search method, but you can implement your own like as an exercise after watching this video. And if we execute the code, we're gonna get that our targets were a lot of random numbers from 1 to 1 million. And if you can see here, the average sequential time is 0.01 for sequential search, which is the one that we go from A to Z. But for binary search, it's 1.8 times 10 to the negative 0, say, times 10 to the negative 6, which is very, very small. That means we have 6 zeros after the decimal point, showing really the vast difference between sequential and binary search. And mind you, this is a list with only 1 million 1 million elements. And you might think that, no, this isn't practical, that you won't have 1 million elements. But really, it is very common for, like, imagine the number of texts in the world that a company could have, like WhatsApp texts. If you're going to sort those, it's going to be way more than 1 million. So this is a low ball by far. And search algorithms really are very applicable everywhere. And binary search isn't an idea that hasn't existed before computers. People use this before computers. If you ever opened a book, you'd usually use it intuitively without knowing that you were trying to use binary search rather than going one, two, three, and four. And it really is an essential element of computer science to find the fastest algorithm for the task. And binary search has proved its ability and really is one of the fastest. And as always, I thank you for your listening, and any feedback is appreciated.